All right, so now we have discussed about the constraint optimization, where before this, you know that you have done with the unconstrained. I have shared with you the video of lecture reef. So that is the last method which have been used in unconstrained optimization. So we have direct search, interpolation, and dimensional and conjugate. Okay. So now we are going to focus on constraint, but this constraint can be solved by deducing to unconstrained. So one of the method is Kantaker, okay? And there are two types of constraint optimization. So the first one is equality, where we have done with Lagrange multiplier. It's quite easy, just adding the lambda there. And then for inequality constraint, okay? So we have been introduced to this Kantaker. So there is one method in order to solve the inequality constraint, okay, which is Kantaker method, Kantaker by using Kantaker condition. All right. So now all of you know the difference between constraint and unconstrained. For constraint, there is a limitation on its boundaries. Okay, for unconstrained, it has no boundaries, or the boundaries will solve just the dotted line like that. Okay, but in constraint optimization, we have a limit placed on the value. So we have a limit on the curve of the objective function, okay, which prevents us from going forever in certain directions. So with nonlinear, we have many types of curve there. With a linear, we have a straight line where we occur the minimum and maximum at the boundary. Okay, so this is the minimum, this is the maximum. For non-linear, the maximum or minimum can be occur anywhere. Okay, so that is the difference. So for equality, we just can use the Lagrange multiplier, okay, where this is the derivation we have discussed last week, where we are going to solve this Lagrange multiplier function, where we have f, we have a function of f in terms of x, y, and lambda, and then we are going to solve this. Okay, solving this will give you a maximum or minimum point which maximize or minimize the objective function. Okay, so we have done with this example where we want to minimize the function subject to the equality constraint. We substitute to the Lagrange multiplier, apply the condition of Lagrange to solve the values of x, y, and lambda. Same with this example, okay? And how can you identify the minimum or maximum? So sometimes it is written here, so you know that the problem is minimum. But if it is not explained, it is not mentioned about the minimum or maximum, we just can test the point by using the Hessian matrix here. Okay. All right. So what is the condition for a minimum? What is the condition for maximum? You can test by using the definiteness of its matrix. Okay. Is that clear for the equality constraint? Any question? We just revise back. Are you listening? All right, all good. Okay, so now let's proceed with inequality constraint. Okay. All right, so in inequality constraint, still we are going to use a concept of Lagrange multiplier, but we need to do some modification in its constraints. All right, so in inequality constraint, sometimes we are going to have less or equal than, greater or equal than, and so on. But the general form should be always use less than or equal. So if you have greater or equal, you just can change the sign by modify the function. Okay, after this, we're going to take a look at the example. Okay, so for this inequality, we have the general form. Okay, so this is the general form of inequality constraint. What we are going to do is to convert to equality by adding slack or supplies. Okay, so xn plus 1. Usually we can use this as u squared. Okay, we use squared there so we can ease the process of differentiation later on. Okay, now this one just adding the slack and surplus, okay, in order to make it equal. Okay, and then we are going to consider which constraints are active or passive. So if we want to take a look at the figure, okay, let's say this is the region of the minimization problem. Okay, we have here constraint 1, constraint 2, constraint 3, constraint 4, okay, constraint 5, constraint 6. So what can be determined by active or passive? Okay, so this constraint touch the region, right? Touch the region of the objective function. So this is what we consider as the active constraint. Okay. All right. And then for those who don't touch the region, we call it as a passive constraint. So this is the difference between active and passive. Okay. So we have the general form of inequality. Okay. We are going to solve this by changing to equality by adding or subtracting the surplus. So this value of slack or surplus here can be divided to two categories, active or passive. Once you add the slack or surplus, we can identify the active or passive constraint. If the variable here equals to 0, means that it is located on the boundary. So this is located on the boundary. That's why we call it as a active constraint. Okay, and if it is greater than where it is not located on the boundary, then we can say that it is a passive constraint. Okay, clear? So now we need to understand the active and passive here so that we can apply to solve it by using Kuhn-Tucker condition after this. Okay, all right, clear now? Anyone has question? Okay, so if it is active, doesn't matter. We just can identify the constraint and then locate its extremum point. But if it is passive, we have to do some calculation. So if the constraint is passive, we are going to use this Lagrange, okay, by introducing xs here where it is a vector for slack or surplus. Okay, so we substitute the problem, the inequality constraint problem, to this Lagrange. Okay, and then we are going to have the solution of lambda here. So that's why when it is passive, the lambda equals to 0. So you are going to use this to apply to the Kuhn-Tucker condition after this. So when it is passive, lambda I equals to 0. Okay, so now we apply this Kuhn-Tucker condition by identifying which constraint is active, which constraint is passive. Okay, so you know that this is inequality. So this is inequality, and you know that in order to solve this, we need to change to equality. Okay, and then by identifying the constraint, you have to check which one is active or passive. So if it is passive, the lambda, okay, when it is passive, the lambda in the Lagrange multiplier equals to 0. Okay, so now we are going to find the solution of this by using Cantucker condition, where we have to consider the criteria for active and passive, because after this, we are going to solve some sort of simultaneous equation. All right. Okay, are we good? So theoretically, this is the Cantucker condition, where we want to differentiate the function f here with respect to x, with respect to lambda, and then what are the conditions that we need to fulfill in order to find the minimum or maximum point. All right. Okay, let's try to understand this by using the example here first. Okay, I'm going to give you another example. So let's say we want to minimize x squared, x1 squared plus x2 squared. Is it same? Okay. Then the condition given is okay. So the general form is always written in terms of less than, greater than, equal. Okay, so it is general. But in order to make it standardized, we need to convert the problem in less than or equal. So if we have greater than, we just can convert this to less than by rearrange the variable. So now this example is already in terms of less than or equal. Okay. So right now the first step, okay, the first step is to have in terms of Lagrange, where the function must consist of x1, x2, lambda, and u. Okay, u here is xs. Okay, is xs in the general form here, where what is xs? Xs is a vector for slack or supplies, because we have to convert the inequality to equality constraint. So now this can be written as what? This can be written as, this is less than. Less than should add or minus, add slack or surplus. Less than. So less than should plus, right? Plus with slack. Okay, here. Okay, let's take a look at this. Let's do this one by one. So we are going to have here. So we just introduce u1 squared equals to 0. So this is a vector of xs. We use u1 squared, just another constant, another variable, okay, in order to ease the differentiation process. Okay, but actually this variable can be any variable. Okay, so to make it standardized, I use u1 squared here. Okay, and then this one, we convert to equality. It can be x2 plus u2 squared. Okay, and then this one, minus x1 minus x2 plus 5. Okay, put it to the left hand side, plus with u3 squared. Okay, so now in terms of Lagrange, we can write this as function f x1 squared plus x2 squared. Then we have what? Lambda 1 u1 squared minus x1 here plus lambda 2 u2 squared minus x2 plus lambda 3 u3 squared minus x1 minus x2 plus with 5. Okay, clear now? So clear not? Anyone has question? Okay, what we are doing just now is what? We change to inequality to quality by adding slack or surplus. How can we identify slack or surplus? By considering the sign of inequality there. So if it is less or equals, then we just plus with another slack. Okay, so now this is F, your Lagrange. And then theoretically, this is the Kuhn-Tucker condition. So how can this Kuhn-Tucker condition is represented in numerical example? Okay, so next, what are the conditions that we have to consider? So first, of course, we need to have del F, del X1. Okay, equals to 0. Del F, del X2 equals to 0. And then what? No more. Okay, so now by looking at the condition of Kuhn-Tucker here, del F, del X equals to 0. This one. Del F, del X equals to 0. Okay, so now we have del F, del X1 is 2x1 minus lambda 1 minus lambda 3 equals to 0. Okay, differentiate F with respect to X1. Another one is 2x2 minus lambda 2 minus lambda 3 equals to 0. Okay, so in Lagrange multiplier for equality constraint, all right, we can just differentiate del F del X, del F del Y, del F del lambda equals to 0 because this is equality. Okay, but by looking at the Kuhn-Tucker condition, we cannot find del F del lambda 1, del F del lambda 2 equals to 0 because we have to consider condition that we need to apply, to implement in the given problem. So what should we do? So by using the Kuhn-Tucker condition, the first one, we just differentiate F with respect to variable x1 or x2. And then we consider another condition where you know that the constraint itself given negative x1 less than 0, negative x2 less than equals to 0, negative x1 minus x2 less than equals to negative 5. And you know that there are two types of constraint. Okay, it can either be active or passive. So how can we identify its activeness or passiveness? By looking at the what? By looking at the slack, but we don't know. So we have to consider this and this. So what we can identify here, where the variable of lambda itself, lambda 1, lambda 2, lambda 3 can either be passive or active. How? By equal them to 0, then it is what? It is active. By equal them to the greater of 0 to consider it is passive. So we can conclude that lambda 1, lambda 2, lambda 3 greater or equals to 0. Okay, is that clear up until here? Anyone has question? Anyone has question? No question. So these are actually Kuhn-Tucker condition. Okay, we have del F del X1, del F del X2 equals to 0. So 1, 2, and then the constraint itself, the constraint, and then the value of lambda. So we need to consider all of this as your Cantucker condition. So if you are asked to write down the Cantucker condition to fulfill the minimum or maximum point, so this is it. Okay, you have to find del f del xi equals to 0. So if you have two variable of x, then you have two equation. And then consider all the constraint of less than or equal than, okay, make it standardized, and then consider the variable of lambda, either can be active or passive by this one. Okay, so we have this condition. So this condition comes from this Cantucker, this theory of Cantucker condition. Okay, what if lambda greater than 0? What if lambda less than 0? So this theory of Cantucker condition is summarized here. Okay, so we have to have del f del xi equals to 0, and then the constraint itself, and then the lambda itself. Okay, now how can we identify which constraint is active or which constraint is passive? Okay, there are two types, right? There are two types of considering which constraints are active or passive. The first method is you can just figurize. Okay, you have to draw the graph and then identify that constraint touch the region or not. Okay, or else you just can have a table of try and error values. Okay, so now let's take a look. So for this problem, you have x1 and x2. You know that it is a circle, right? X1 squared plus x2 squared. Okay, we have here x1, we have here x2. Okay, negative x1 less than 0, negative x2 less than 0, and then we have negative x1 minus x2 negative 5. So this is the constraint. Okay, then negative x1 less than 0 is here, negative x1. This is negative x2, this is negative x1. Okay, and then the constraint here touch the region of the circle. So this is what we call as a active constraint. All right, and this one does not touch. It's just equality region. Okay, so we can consider this negative x1 and negative x2 as passive. Okay, now when it is passive, what happened? When it is passive, we have discussed this. When it is passive, then we can conclude that lambda I equals to 0. When it is active, that value of lambda cannot be equals to 0. So it should be what? Greater than 0. Okay. So now let's take a look at the active constraint. So here, this is considered active, means that this involve what? This constraint involved with lambda 3. Okay, when this constraint is considered active, where this constraint involve lambda 3, then what we can say here is lambda 1, lambda 2 equals to 0, lambda 3 greater than 0. Okay, clear now? Why this is equals to 0? Because this is passive. This is considered active. Okay, clear now? Any question? Okay, are you with me, guys? All of you understand this? Anyone has question? Faham tak ni? Okay. So now, by looking at the condition here, when you consider that lambda 1 and lambda 2 is passive and is 0, what you can have here from the equation, from this equation, 2x1 minus lambda 1 minus lambda 3 equals to 0. 2x2 minus lambda 2 minus lambda 3 equals to 0. And this is passive. So you just consider this is 0, this is 0. Okay? Then you can solve this. 2x1 minus lambda 3 equals to 0. 2x2 minus lambda 3 equals to 0. So solving this will give you the value of x1 and x2. And then once you obtain the value of x1 and x2, you can find the value of f. Okay, so from here you can obtain x1 2.5, x2 equals 2.5. So substitute to the value of f will give you 12.5. Okay, and then for this example, we know that the lambda here is passive and the lambda here is active. So we just can have our minimum value and minimum point. But if we don't know the value of lambda, which lambda is passive or active, we need to test. Okay, maybe lambda 1, lambda 2 equals to 0. What happened to lambda 3? And then another test, lambda 1 and lambda 3 equals to 0. Then what happened to lambda? So you need to write down one by one. Okay, so that one is if you don't know which lambda or which constraint are active or passive. But if you know directly from the figure, okay, which constraint touch the boundary, then it is an active constraint. Then we just can assume that the rest of the constraint is passive, where the value of lambda is 0. Then we just can have the value of x1 and x2 there. Okay, clear now? Any question? Okay, so how can you find the value of x1 and x2 here? By considering this one, right? This is already 0. This is already 0. So we consider this. Okay, when this one lambda 3 greater than 0 means that this one can be written as minus 1 minus x2 plus 5 equals to 0. So solving this and this will give you the value of x1 and x2. Okay, so no question. Let's try the previous example that we have discussed last class, in our last class here. Okay. So we have negative, 3x1 squared plus 4x1 x2 plus 5x2 squared. Okay. Now you have the constraint of greater or equal than here. So what you have to do from here is to convert this to less than. Okay, then you can have your Lagrange, right? You can have your Lagrange by putting lambda 1 with the first constraint, lambda 2 with the first constraint, lambda 3 with the third constraint. Okay, and then we differentiate del f del x1, del f del x2 equals to 0 and equals to 0. Okay, so these are the Kuhn condition. where you just list down again the constraint given. Okay, and then we consider that these constraints are all equals to 0 here. Okay, just like this one. Okay, now what we can identify is which constraint is active and which constraint is passive. So the easiest method is you just can plot. All right. So 3x1 plus 4x1 x2 plus 5x2. You know that this is can be written in can be plotted in terms of curve. Okay, the contour here, and you can see that the third constraint touch the region. So lambda 3 greater than 0, and then the rest of the constraint does not touch, so we consider it as a passive. Okay, and then we just can solve the value of x1 and x2, and then we can have the value of f there. So this is same with the example that we have discussed earlier. Okay, so this is how can we solve the inequality constraint by using Kuhn-Tucker condition. Okay, clear or not? Clear or not, guys? Anyone has question? Okay, so if you don't know how to plot, okay, that is one of the problems. Okay, you can try and error with a table of lambda value. So let's say for this example, you just can list down what is your lambda. All right. So let's say lambda equals to 0, and then this one greater than 0, greater than 0. What happened to the x1 and x2? So you just need to do it one by one. If this one is 0, this one is 0, this one is greater than 0, then what happened to x1 and x2? You just can find your value of f there. Okay. So you need to test one by one, which is quite a messy calculation if you have to test one by one, but that is the process. So usually for this type of Kuhn-Tucker condition here, our focus is on to identify the condition. So it is not advisable for me to ask you directly based on lambda value here. Otherwise, it is not quite suitable for a numerical calculation. Okay, because it takes a long of time to consider or to test the values of lambda 1, lambda 2, and lambda 3. So maybe it can be plotted directly and you can identify which constraints are active. Then just consider the passive one equals to 0 and then solve the problem. All right, is that clear? Anyone has question? Minus. Okay, try this one. Try this one. Try this example. First, you know that you have to change the constraint to less than, okay, to make it standardized. And then you just can act with the slack, where our slack used here is in terms of ui squared, okay? And then just list down all the condition. And directly you can see that this constraint will touch the region. So this is active constraint. This is passive. Okay, try to identify the values of x1, x2, and lambda 3. What is your f? What is your del f del x1, del f del x2? And then equate them to 0 to list down, and then list down all the Cantaco condition. All right, can you? All right, so we have this inequality problem where it is in terms of greater or equals and less than equal. So in order to standardize this, just change all of it to less or equal, and then we add the slack variable in order to make it equality constraint. So once it is in terms of equality constraint, then we just can use the Lagrange multiplier, where it is in terms of f x, y, lambda, and u here. Okay, f is minus x squared minus y squared plus with our lambda 1 minus x plus u1 squared plus with lambda 2 minus y plus with u2 squared plus with lambda 3 x plus 2y minus 3 plus u3 squared. Okay, and then the Cantaco condition is del f del x1, del f del x equals to 0, where it is minus 2x minus lambda 1 plus lambda 3. Just differentiate f here with respect to x equals to 0. Then we have del f del y minus 2y minus lambda 2 plus 2 lambda 3 equals to 0. Okay, and then we have the inequality itself, minus x less or equals to 0, minus y less equals to 0, and x plus 2y less or equals to 3. Okay, and then another condition is lambda 1, lambda 2, lambda 3 greater than 0. And we have lambda 1 x equals to 0, lambda 2y equals to 0, lambda 3x plus 2y minus 3 equals to 0. So these are the Cantaco condition that you have to list down. The derivative itself, the inequality itself, the value of lambda that we need to consider because we don't know which constraints are active or which constraints are passive. And then the constraint together with the lambda. So now you know that, okay, I have mentioned earlier, you know that this is passive, this is constraint. When this is passive, these two are passive, you know that lambda 1 and lambda 2 both equals to 0. So we have lambda 3 greater than 0. Okay, so how can we solve this? So we just can identify here lambda 1 and lambda 2 equals to 0, where we can have negative 2x plus lambda 3 equals to 0, minus, we can have the equation here, minus 2x minus lambda 3 plus equals to 0, minus 2y plus 2 lambda 3 equals to 0, and then this one we have x plus 2y minus 3 equals to 0. When this is greater than 0, means that it is not 0. We just can put this to the right hand side, and then we have left with this one. So you can solve these three equations. We have three variables, three equations. We can identify the value of x, y, and lambda, and then the value of f. Okay. All right. Can you do this? What is x, y, and lambda here? Anyone? I don't have my calculator with me. Let me check. Minus 9 over 5. Which one? Minus 9/5 for what? What is your x, y, and lambda there? Lambda 3. All right. Okay, x equals to 3/5. Now y equals to 6/5. Lambda 3 equals to 6/5. So substitute this, and then you can have your f value. If you have a list of points, you just can substitute all of it, and then we consider the most minimum or the most maximum value to be your solution point. Okay, is that clear? Anyone has question? Macam mana nak tahu lambda 1 and 2 equals to 0? So first, you need to identify which constraints are active or passive. So if the constraints are passive, then automatically that lambda equals to 0. But if you don't know, you can have a test of value. Let's say we start with lambda 1 equals to 0, lambda 2 or lambda 3 greater than 0. Or lambda 1 and lambda 2 equals to 0, lambda 3 greater than 0. Or lambda 3 only equals to 0 and so on. So you can have a test. Okay, that one is the first method. Or else you can plot. Okay, you can plot the objective function there, and then you have to plot all the constraint, which constraint touch the boundary, touch the region of your objective function. Okay, so if it is touched, then it is active. Then active means greater than 0. Okay, when it does not touch, then it is passive. Then automatic that lambda equals to 0. Okay, clear? Okay, any more question? So that is it for Kuhn-Tucker condition. Okay, the problem here is to identify which constraint is active, which constraint is passive in order to determine which lambda is 0 or not. Okay, so from there, you just can solve the equation simultaneously. All right. Okay. Last week, example last week, mana? Yang ini. Yang ini kan? Is it? Yang ini I ada bagi dekat e-learning. Dia punya file tu. Tak silap lah. Cuma explainnya I baru explain tadi. Okay.